For 3 decades, our view of the cosmos was defined by a single magnificent instrument, the Hubble Space Telescope. It was our eye on the universe, a window that revealed the beauty and the majesty of creation in ways we had never imagined. But for all its power, Hubble could only see so far. It showed us a universe of brilliant, mature galaxies, but the very first chapters of the cosmic story, the dawn of the first stars and the birth of the first galaxies, remained hidden from its view, shrouded in a veil of time and distance. But now, a new eye has opened onto the cosmos. A golden eye, 100 times more powerful than Hubble, an engineering marvel that has been designed to see the invisible. Tonight, we explore the universe through this new window. We will journey back to the dawn of time to witness the impossible birth of the first galaxies. We will peer through impenetrable clouds of dust to see infant stars being born, and we will taste the air of worlds light years away. Prepare to see the universe as you have never seen it before. Prepare to see what the James Webb Space Telescope is really seeing. The story of the James Webb Space Telescope, or JWST, is not a story of years, but of decades. It is a testament to the long, patient, and audacious ambition of human science. The vision for this telescope was born before Hubble had even left the ground. In the late 1980s, astronomers were already dreaming of what would come next. They knew that Hubble, a masterpiece of visible and ultraviolet light astronomy, would revolutionize our understanding of the universe. But they also knew it would have fundamental limits. It would show us the what, but it would not be able to show us the how or the when of our ultimate cosmic origins. The dream was for a successor, a telescope that could answer the profound questions that Hubble was not designed to ask. How did the first galaxies form out of the darkness of the cosmic dawn? When did the first stars ignite, ending the universal dark ages? How are stars and planets born inside their dusty, opaque cocoons? And are there other worlds out there that might harbor the chemical ingredients for life? To answer these questions, we would need a new kind of observatory, one that could see the universe not in visible light, but in the invisible, ancient, and heat-carrying light of the infrared. This was the vision that would, over the next 30 years, grow into the James Webb Space Telescope. It was a project of unprecedented scale, complexity, and cost. It would push the boundaries of engineering and technology in every conceivable way. It would require a mirror larger than any that had ever been launched into space. A mirror so large it would have to be folded up like origami to fit inside a rocket. It would require a sunshield the size of a tennis court, made of a material as thin as a human hair to keep the telescope at a cryogenically cold temperature. And it would need to be sent not into orbit around the Earth, like Hubble, but to a lonely, isolated point in space, 1.5 million kilometers away, a place from which it could never be repaired. The journey of the JWST from a dream to a reality was a long and often difficult one. It faced budget overruns, technological setbacks, and multiple threats of cancellation. It was a project that tested the will and the ingenuity of thousands of scientists and engineers across the globe. It was a multi-generational effort, a scientific cathedral that took longer to build than many of the great cathedrals of the medieval world. But on December 25th, 2021, that 3-decade-long dream was finally realized. The James Webb Space Telescope was launched flawlessly from French Guiana, folded up inside an Ariane 5 rocket. It then began a month-long, nail-biting, and ultimately perfect process of deployment and commissioning. The world watched as the great golden mirror unfolded, as the giant sunshield unfurled, and as the telescope cooled down to its operating temperature. When the first images were finally released to the world, in July of 2022, they were a revelation. They were a quantum leap beyond anything we had ever seen before. They were deeper, sharper, and more detailed than we had dared to hope. They were the fulfillment of a 30-year-old promise. The new golden eye was open, and it was ready to show us a universe we had never seen before. To understand the revolutionary power of the James Webb Space Telescope, we must first understand the invisible light it is designed to see. JWST is not a visible light telescope like Hubble. It is an infrared telescope. Infrared light is a form of light that is just beyond the red end of the rainbow that our eyes can see. We feel it on our skin as heat, and for an astronomer, the ability to see in the infrared is not just an advantage, it is a superpower. It allows them to do two things that are impossible for a visible light telescope to travel back in time and to see through walls. The first of these superpowers, the ability to travel back in time, is a consequence of the expansion of the universe itself. The universe is not static. It has been expanding ever since the Big Bang. This expansion means that the space between the galaxies is constantly stretching. As the light from a very distant galaxy travels across billions of light years to reach us, the space it is traveling through is stretching out beneath it. This stretching of space, in turn, stretches the wavelength of the light itself. It's an effect known as cosmological redshift. It is very similar to the Doppler effect for sound. Imagine the siren of an ambulance. As the ambulance moves towards you, the sound waves are compressed, and the pitch sounds higher. As it moves away from you, the sound waves are stretched, and the pitch sounds lower. For light, this stretching is a shift towards the red end of the spectrum. The farther away a galaxy is, the faster it is receding from us due to the expansion of space, and the more its light is redshifted. The very first stars and galaxies in the universe were born about 13.5 billion years ago. They were likely massive, brilliant, and blue, emitting most of their light in the energetic visible and ultraviolet parts of the spectrum. But over their 13.5 billion year journey to us, the universe has expanded by a factor of more than 10. The light from these first galaxies has been so stretched, so redshifted, that by the time it reaches our telescopes, it is no longer visible light. It has been shifted all the way into the infrared portion of the spectrum. This is why Hubble cannot see them. Hubble is like an eye that can only see visible light. The light from the first galaxies is invisible to it. To see the cosmic dawn, to witness the birth of the very first structures in the universe, you need an eye that can see in the infrared. You need the James Webb Space Telescope. It is a time machine designed specifically to capture this ancient, stretched, and redshifted light from the beginning of all things. The second superpower of infrared light is its ability to penetrate through the dense clouds of gas and dust that permeate our galaxy. The beautiful glowing nebulae that Hubble photographs so well are often the sites of active star formation. But the actual birth of stars and planets happens deep inside the coldest, densest, and darkest parts of these clouds, in regions that are completely opaque to visible light. A visible light telescope looking at one of these stellar nurseries is like trying to look into a smoky room. You can see the smoke, but you cannot see what is happening inside. Infrared light, however, has a longer wavelength than visible light. This longer wavelength allows it to pass through the tiny dust grains in these clouds much more easily, without being scattered or absorbed. Infrared light can see through the dust. An infrared telescope, like JWST, can peer deep into these dark, dusty cocoons and see the infant stars and nascent planetary systems that are hidden within. It can give us our first clear view of the birth of worlds, including our own. This is the magic of infrared. It is the light of the ancient past, and it is the light that reveals the hidden process of creation. To be a successful infrared telescope, the James Webb Space Telescope has to be one of the coldest objects in the entire solar system. Infrared light is heat radiation. Any object that has a temperature above absolute zero will emit its own infrared light. If the telescope itself were warm, it would be blinded by its own glow, like trying to take a picture of a faint star while standing inside a brightly lit room. To see the faint infrared signals from the distant universe, JWST must be kept cryogenically, unimaginably cold. Its operating temperature is below -223 degrees Celsius, or -370 degrees Fahrenheit. This single brutal requirement dictated every aspect of the telescope's audacious and revolutionary design. The first and most iconic feature is its magnificent primary mirror. It is a honeycomb of 18 hexagonal segments, made of the lightweight and durable metal beryllium and coated in a microscopically thin layer of pure gold. Gold is an almost perfect reflector of infrared light. This mirror is 6.5 meters, or 21 feet, across, giving it more than 6 times the light collecting area of Hubble's mirror. A mirror this large could not be launched in one piece. It had to be designed to fold up, like the leaves of a drop-leaf table, to fit inside the rocket fairing and then unfold itself with nanometer precision once in space. But the true key to keeping the telescope cold is not the mirror itself, but the colossal and beautiful structure that flies beneath it, the sun shield. The sun shield is a 5-layer kite-shaped membrane, the size of a tennis court. Each layer is made of a special material called captin and is coated in aluminum and doped silicon, and each layer is as thin as a human hair. The sun shield is the telescope's parasol, its ultimate protection from the light and heat of the sun, the earth, and the moon. As the telescope travels through space, the sunshield is always positioned between the warm sunlit side, where the spacecraft's bus and solar panels reside, and the cold, dark side, where the mirror and the scientific instruments are. The 5 layers are separated by a vacuum, which is a perfect insulator. Each successive layer of the shield radiates heat out into space, getting progressively colder. The difference in temperature between the hot sun-facing side of the shield and the cold telescope side is almost 300 degrees Celsius. It is a masterpiece of thermal engineering, a giant passive refrigerator that allows the telescope to cool down to its frigid operating temperature, and to ensure that the sun, Earth, and Moon are always on the same side of the spacecraft. JWST could not be placed in orbit around the Earth, where it would constantly be moving in and out of our planet's heat and shadow. It had to be sent to a very special and very distant location in space. This is the second Lagrange point, or LO2. LO2 is a gravitationally stable point, located 1.5 million kilometers, or nearly 1 million miles, away from the Earth, in the direction opposite the Sun. An object placed at L2 will orbit the Sun in perfect lockstep with the Earth, taking exactly 1 year to complete one orbit. From this vantage point, the Sun, the Earth, and the Moon are always in the same part of the sky, allowing the telescope to keep its sunshield permanently pointed towards them, and its golden mirror permanently pointed out into the cold, dark abyss. The journey to L2 was a month-long and nail-biting voyage. During this trip, the telescope had to perform the most complex series of deployments ever attempted for a robotic space mission. The sunshield had to be unfurled and tensioned. The secondary mirror had to be deployed on its long tripod. The 2 side wings of the primary mirror had to fold into place. There were over 300 single points of failure, any one of which could have doomed the $10 billion mission. But the deployment was flawless. The journey was perfect. The James Webb Space Telescope arrived at its lonely, dark, and cold home at LRS-2, a true chariot of the gods, ready to begin its long-awaited exploration of the invisible universe. When the first full-color images from the James Webb Space Telescope were released to the world, there was one that, more than any other, captured the public's imagination and demonstrated the breathtaking power of this new observatory. It was a landscape of cosmic mountains and valleys, a celestial seascape of swirling gas and dust, glittering with the light of hundreds of previously unseen stars. This was the image of the cosmic cliffs, a small section of the vast and turbulent Carina Nebula. The Carina Nebula is one of the largest and brightest star-forming regions in our entire galaxy, located about 7,600 light-years away. It is a colossal cloud of gas and dust, a stellar nursery where some of the most massive and luminous stars in the Milky Way are being born. The Hubble Space Telescope has photographed this nebula many times, producing stunning and iconic images. But Webb's view of the same region was a revelation. It was like seeing a familiar landscape with a new set of eyes that could see through the veil of dust and into the very heart of creation. The image shows the edge of a giant gaseous cavity within the nebula. The mountains and cliffs are the boundary wall of this cavity, a wall of dense molecular gas and dust that is being carved and sculpted by the intense, ferocious ultraviolet radiation and stellar winds from a cluster of massive young blue stars that are located just off the top of the image. In Hubble's visible light view, this region is a beautiful, but largely opaque, wall of glowing gas. We can see the surface of the cloud, but we cannot see what is happening inside it. But in Webb's infrared view, the cliffside becomes a translucent, shimmering curtain of orange and brown. The infrared light penetrates through the dust, and suddenly, the interior of the cloud is revealed in all its glorious detail. The most breathtaking revelation is the hundreds of tiny red and pink points of light that are scattered throughout the gas and dust. These are not background stars. These are protostars, infant stars that are still in the process of being born, still hidden within their dusty natal cocoons. Webb's infrared vision has for the first time allowed us to pierce these cocoons and see the baby stars directly. We can see powerful jets of material being blasted out from the poles of these young stars. These are the energetic outflows that are a signature of the star formation process. We can see the dark, dense globules of gas that are on the verge of collapsing to form the next generation of stars. We can see the protoplanetary disks of dust and gas that are forming around some of these young stars. The image is not just a pretty picture, It is a single information-rich frame that tells the entire story of the star formation cycle. We see the raw material of the dense cloud. We see the destructive sculpting power of the massive stars that have already formed. And we see the next generation of stars, just beginning to ignite deep within the cloud, their birth triggered by the compression of the very same stellar winds that are eroding their nursery. The cosmic cliffs image is the perfect demonstration of Webb's second superpower, its ability to see through dust. It is a new window onto the hidden, chaotic, and breathtakingly beautiful process of stellar birth. It is a family portrait of the stars, showing us the brilliant, unruly teenagers, the glowing, newborn infants, and the dark, pregnant clouds that are still waiting to give birth. While Webb's images of stellar nurseries have been breathtaking, its most scientifically profound and paradigm-shifting discoveries have come from its other primary mission, to peer back to the dawn of cosmic time and find the very first galaxies. For decades, our cosmological models, based on our understanding of dark matter and gravity, have made clear predictions about what the early universe should look like. It should have been a time of slow, patient growth, where small, wispy, and irregular protogalaxies slowly merged and grew over hundreds of millions of years into the larger, more structured galaxies we see today. The James Webb Space Telescope was designed to confirm this picture, to find these faint first galaxies and watch them grow. But in its first year of operation, Webb has found something completely different, something that is wonderful, mysterious, and deeply unsettling for our established theories. The baby galaxies of the early universe are not small, wispy, and clumpy. They are shockingly, impossibly big. Webb has been able to find galaxies that were shining just 3 to 400 million years after the Big Bang, when the universe was only 2% of its current age. These are the most distant and most ancient galaxies ever seen by humanity, and they are not what we expected. Many of them are as massive as our own Milky Way galaxy is today. They are bright, they are well-structured, with clear evidence of spiral disks, and they seem to be filled with populations of older, redder stars. This is a cosmological crisis. It is like looking at a photograph of a 2-year-old child and finding that they are already 6 feet tall and have a full beard. It shatters our timeline of cosmic evolution. How could the universe have built such massive, mature galaxies so incredibly quickly? Our current models of galaxy formation, which rely on the slow, hierarchical merging of smaller structures, simply do not have enough time to build such monsters so early in the universe's history. These discoveries, made by programs like the JWST Advanced Deep Extragalactic Survey, or JADES, have sent theorists and cosmologists scrambling for an explanation. The universe appears to have been far more efficient at building galaxies in its youth than we ever thought possible. Several new and exciting theories are now being explored. Perhaps the first stars, the so-called population 3 stars, were far more massive and far more efficient at creating heavy elements than we thought, providing the raw materials for rapid galaxy growth. Another, more radical idea is that the supermassive black holes at the centers of galaxies formed first, and formed big. Instead of the galaxy forming and then growing a black hole, perhaps colossal black holes with the mass of 1 million suns formed directly from the collapse of primordial gas clouds in the early universe. These giant black holes would then have acted as powerful gravitational seeds, rapidly pulling in gas and triggering furious bursts of star formation around them, building a massive galaxy in a very short amount of time. This black hole first model is a radical departure from our standard picture, but it is one that the strange and beautiful data from Webb seems to support. The impossibly early galaxies are not just a curiosity, they are a profound clue. They are a signpost from the dawn of time that is telling us we are missing a fundamental piece of the cosmic puzzle. The story of our universe's birth appears to be far more dramatic, more violent, and more rapid than we ever dared to believe. While Webb is a powerful time machine for studying the distant universe, it is also a revolutionary tool for exploring the worlds in our own galactic backyard. One of its other primary missions is to study the atmospheres of exoplanets, planets orbiting other stars, and to search for the chemical fingerprints that might hint at their composition, their climate, and even their potential for life. To do this, Webb uses a technique of almost magical precision called transmission spectroscopy. This technique can only be used for a specific class of exoplanets, those whose orbits we happen to see edge on, so that the planet performs a transit or passes in front of its parent star. From our point of view, when a planet transits, it blocks a tiny fraction of the starlight, causing a small temporary dip in the star's brightness. This is how most exoplanets, including those found by the Kepler mission, are discovered. But Webb takes this a step further. It is so sensitive that it can analyze the starlight after it has passed through the thin gaseous limb of the planet's atmosphere. Imagine a tiny backlit halo of air around the planet. The starlight that passes through this halo will carry with it the chemical fingerprint of the gases in that atmosphere. Different molecules in the atmosphere, water, carbon dioxide, methane, will each absorb the starlight at their own unique characteristic set of infrared wavelengths. When Webb observes a transit, its spectrographs spread the starlight out into a rainbow, or spectrum. By looking for the tiny dark absorption lines in this spectrum, the specific colors that are missing, astronomers can deduce with incredible precision exactly which molecules are present in that distant world's atmosphere. Webb is, in essence, sniffing the air of a planet that is trillions of kilometers away. In its first year of science, Webb has already used this technique to revolutionize the field of exoplanet atmospheres. One of its first and most celebrated targets was the hot Jupiter WASP-39b. Previous observations had hinted at the presence of water vapor, but Webb's spectrum of this world was a revelation. It provided the first ever, absolute, and undeniable detection of carbon dioxide in the atmosphere of an exoplanet. It also found evidence for sulfur dioxide, a molecule that is likely created by photochemical reactions, meaning Webb is not just detecting chemicals, but is seeing active chemistry happening in the planet's atmosphere. On another hot Jupiter, WASP-17b, Webb made an even more startling discovery. It found that the planet's clouds are not made of water, as they are on Earth, or ammonia, as they are on Jupiter. They are made of microscopic crystals of quartz, the same silicate mineral that makes up sand and glass. It is a world with clouds of sand, and for the now famous TRAPPIST-1 system, a system of 7 rocky, Earth-sized planets orbiting a nearby red dwarf star, Webb has begun the long and patient process of studying their atmospheres, or lack thereof. For the innermost planet, TRAPPIST-1b, Webb has found that it has no significant atmosphere at all, likely having been stripped away by its parent star. This is a crucial, if sobering, data point in our assessment of the habitability of planets around red dwarfs. This is just the beginning. Over its long mission, Webb will continue to stare at hundreds of transiting exoplanets, from hot gas giants to most tantalizingly small, rocky, temperate worlds in the habitable zones of their stars. It will be searching for the chemical signatures of water, methane, and other gases that could be potential biosignatures, hints that we are not alone. Webb is not just a telescope, it is a remote astrobiology laboratory, and it has opened a new and breathtaking chapter in our long and enduring quest to find another world like our own. Beyond the grand, programmatic goals of cosmology and exoplanet science, the James Webb Space Telescope is also an unparalleled tool for discovery, an instrument designed to look at familiar objects with new eyes and reveal the hidden structures and processes that have been invisible to us until now. Two of its most spectacular early images, one of a ghostly phantom and one of a fiery wheel, perfectly illustrate this incredible power to reveal the unseen universe that lies hidden behind a veil of dust. Our first destination is the Phantom Galaxy, officially known as Messier 74. This is a magnificent face-on spiral galaxy located about 32 million light-years away. It is a grand design spiral, meaning its spiral arms are prominent, well-defined, and almost perfectly symmetrical. In visible light, as seen by Hubble, the Phantom Galaxy is a beautiful, ethereal object. Its arms are traced by the brilliant blue light of young massive stars, and they are modeled by dark, intricate lanes of cosmic dust. But when Webb turned its infrared eye on this same galaxy, a completely new and even more intricate structure was revealed. The dark lanes of dust, which were opaque and obscuring in Hubble's view, became the brightest and most prominent features in Webb's. In the infrared, the dust itself glows with heat. Webb's image revealed that the galaxy's spiral arms are not just defined by stars, but have a delicate filamentary and glowing skeletal structure of gas and dust that lies within them. It is like looking at an X-ray of a living organism. Hubble showed us the beautiful skin, the brilliant stars. Webb has shown us the bones, the glowing, intricate network of gas and dust from which those stars are born. We can see the glowing hearts of star-forming regions deep within the arms, previously hidden from view. We can see the delicate web-like structure of the interstellar medium as it is being compressed and shaped by the galaxy's density waves. The image is a masterpiece of galactic anatomy, revealing the hidden engine of star formation that shapes this beautiful spiral city. Our second destination is an even more dramatic and violent object, the Cartwheel Galaxy. Located 500 million light-years away, the Cartwheel is a rare and spectacular type of galaxy known as a ring galaxy. It was not born with this strange shape. It was the victim of a cosmic hit-and-run. About 200 million years ago, a smaller intruder galaxy passed directly through the center of what was once a normal large spiral galaxy. The collision sent a powerful expanding shockwave of gas and dust ripping through the galaxy, like the ripple created by throwing a stone into a still pond. This expanding ripple triggered a furious burst of star formation, creating the brilliant blue outer ring that we see today. In visible light, the heart of the Cartwheel Galaxy is almost completely obscured by a thick, dense shroud of dust, the chaos and debris left over from this colossal collision. But once again, when Webb turned its infrared eye on the Cartwheel, the dust became transparent, and the true, violent heart of the galaxy was revealed. Webb was able to see through the dust and resolve the individual stars and star-forming clumps in the galaxy's chaotic central region. It also revealed a dramatic difference between the smooth, older population of stars in the galaxy's core and the clumpy, chaotic star formation that is happening in the expanding outer ring. Webb's view of the Cartwheel is a snapshot of a galaxy in the midst of a violent and spectacular transformation. It is a cosmic crime scene, and Webb's infrared vision has given us the forensic tools to analyze the aftermath of the collision in unprecedented detail. These two images, of the Phantom and the Cartwheel, are a perfect illustration of Webb's power. It is a telescope that is not just showing us new things, but is showing us the familiar things in a completely new light, revealing the hidden, dusty, and often violent processes that shape the beautiful cosmic structures we thought we knew. The James Webb Space Telescope was designed to be a time machine, a tool to look back at the most distant and ancient objects in the cosmos. Its incredible sensitivity and its infrared vision are optimized for capturing the faint, red-shifted light of the early universe. And yet, this magnificent observatory is also a powerful tool for looking at the familiar objects in our own cosmic backyard. When Webb turns its golden eye away from the distant cosmos and looks back at our own solar system, it reveals a new and breathtaking layer of beauty and complexity in the worlds we thought we knew. One of its most spectacular early targets was the king of our solar system, the planet Jupiter. While we have studied Jupiter for centuries with ground-based telescopes, and for decades with dedicated spacecraft like Galileo, Juno, and Voyager, Webb's infrared view revealed the gas giant in a completely new light. The images it produced are not the familiar cream and orange globe, but a stunning, ethereal, and almost alien portrait, painted in the unfamiliar colors of infrared. In Webb's view, the Great Red Spot, a storm larger than our entire planet, appears as a brilliant, almost white feature. This is because it is a high-altitude storm, and its towering clouds are reflecting a large amount of sunlight. The familiar colored bands and zones of the planet are transformed into a complex, swirling tapestry of bright and dark regions, revealing the intricate temperature and altitude differences in the planet's churning atmosphere. But the most stunning features in Webb's Jovian portrait are the auroras. Just like on Earth, Jupiter has powerful auroras at its north and south poles. Webb's images captured these auroras in unprecedented detail, showing them as brilliant, glowing rings of light hovering high above the planet's poles. We can see intricate arcs and streamers within these auroral rings, a direct visualization of the complex interaction between the solar wind, Jupiter's colossal magnetic field, and the gases of its upper atmosphere. Webb also captured the faint inner rings of Jupiter, which are almost impossible to see in visible light, and even two of its small faint moons, Amalthea and Adrastea. Webb has also given us a new perspective on the ice giants, Uranus and Neptune. Its images of Neptune revealed its faint, dusty rings with a clarity we have not seen since the Voyager 2 flyby in 1989. It also captured bright, high-altitude methane ice clouds, signatures of the powerful storms that rage in that planet's deep blue atmosphere. Its view of Uranus was equally spectacular, showing a planet tilted on its side, with a brilliant, bright polar cap and a series of magnificent shimmering rings. Perhaps most excitingly, Webb is a powerful tool for studying the smaller, fainter, and more mysterious objects in our solar system. It has studied the strange, hazy atmosphere of Saturn's largest moon, Titan, helping scientists map its clouds and search for changes in its weather patterns. And it is being used to study the distant icy bodies of the Kuiper Belt, the realm of dwarf planets and primordial relics beyond the orbit of Neptune. Because these objects are so far from the Sun, they are incredibly cold and faint, making them ideal targets for an infrared telescope. Webb spectrographs can analyze the faint reflected sunlight from their surfaces to determine their composition, searching for the frozen water, methane, and other ices that hold the chemical secrets to the formation of our entire solar system. While Webb's primary mission is to look out at the great dark ocean of the cosmos, its occasional glances back at our own local island are a powerful reminder of its versatility. It is not just a tool for cosmology, it is a powerful planetary science machine, giving us a new and more profound understanding of the beautiful, strange, and familiar worlds that we call home. The James Webb Space Telescope is not just an observatory, it is a sentinel. Its constant, unwavering gaze upon the cosmos means that sometimes it is in the right place at the right time to witness the most spectacular and violent events in the universe. In May of 2023, such an event occurred. A new star appeared in the sky, a brilliant point of light in the beautiful spiral arms of the nearby pinwheel galaxy, Messier 101. This was supernova 2023 Mix V, the explosive death of a massive star, and the closest supernova to Earth in over a decade. A supernova is the cataclysmic end for a star much more massive than our Sun. After millions of years of fusing heavier and heavier elements in its core, the star finally creates a core of iron, the ultimate stellar ash. At this point, fusion ceases, and the core collapses under its own immense gravity, triggering a titanic explosion that blasts the star's outer layers into space, an event that can briefly outshine an entire galaxy. These events are rare and unpredictable. To study one in detail, and to understand what happens to a star in the final moments before it dies, is the holy grail for astronomers. And with supernova 2023 Pix-5, we got incredibly lucky. Because the Pinwheel Galaxy is a frequent target for astronomers, it had been observed many times by both the Hubble Space Telescope and, more recently, by the James Webb Space Telescope before the explosion occurred. This means we have a before and after picture. We have a pristine cosmic crime scene. In the Baller, images from Hubble, astronomers were able to identify the specific star that was destined to explode. It was a red supergiant, a bloated, relatively cool and massive star, exactly the kind of star we would expect to go supernova. But when astronomers looked at the Baller images from Webb, they saw something Hubble could not. Webb's infrared vision revealed that the red supergiant was surrounded by a thick, dense shell of dust. This dust was glowing with heat, a clear sign that it had been ejected from the star itself. This was the smoking gun. It meant that in the final years and decades leading up to its catastrophic explosion, the star was not stable. It was in its death throes. It was undergoing a period of intense mass loss, puffing away its outer layers and shrouding itself in a dusty, self-made cocoon. This pre-supernova superwind is a crucial but poorly understood phase of a massive star's life, and Webb was able to see it with perfect clarity. This discovery is a game changer. It suggests that many massive stars may not die in a single sudden explosion, but instead go through a sputtering, unstable, and messy end-of-life phase. Webb's ability to see the warm glow of this ejected dust gives us a new and powerful tool to identify stars that are on the verge of going supernova. We might be able to move from being reactive supernova observers to proactive ones, identifying the stars that are about to die and watching them in their final dramatic moments. The story of supernova 2023 XF is still being written. Webb and other telescopes will continue to watch the expanding remnant of the explosion, studying the elements that were forged in its heart and blasted out into the galaxy. It is a real-time, unfolding story of cosmic death and creation, and the James Webb Space Telescope, our new sentinel in the dark, is giving us a front-row seat. The James Webb Space Telescope was designed to answer some of the deepest questions in cosmology. But perhaps the most exciting part of any new observatory is not in the answers it was designed to find, but in the new, completely unexpected questions it forces us to ask. The history of astronomy is filled with serendipitous discoveries, with strange and unexpected objects that challenged our theories and opened up entirely new fields of research. And in its first year of operation, Webb has already given us its own beautiful cosmic enigma. It has found a cosmic question mark. The discovery was made in the background of a stunning image of a pair of young, still-forming stars known as Herbig-Haro 4647s. The main subject of the image was a spectacular display of the powerful jets of gas and dust being blasted out by these infant stars. But deep in the background of this image, far beyond the stellar nursery, lurking in the deep black void, astronomers noticed a small, faint, but unmistakable shape. It was an object that looked, for all the world, like a perfectly formed reddish-orange question mark. What is this strange and whimsical object? The honest answer is that we do not yet know for sure. The object has not yet been the subject of a detailed, peer-reviewed scientific study, but its shape is so tantalizing that it has sparked a wave of speculation and excitement among astronomers and the public alike. The leading and most plausible explanation is that we are looking at a chance alignment of two, or perhaps three, distant galaxies. The top curved part of the question mark is likely a large, distorted spiral galaxy. Its beautiful curved shape is the result of a gravitational interaction, a cosmic dance with a nearby companion. As two galaxies pass close to each other, their mutual gravity can pull and stretch them, drawing out long, beautiful, and arcing tidal tails of stars and gas. The bright, curved hook of the question mark is almost certainly one of these tidal tails, a river of stars being torn from its parent galaxy. The small, distinct dot at the bottom of the question mark is likely a second, smaller and more compact spherical galaxy that is interacting with the first. It is the gravitational culprit, the object whose close pass is responsible for drawing out the beautiful question mark-shaped tail from its larger neighbor. The reddish color of the objects suggests that they are very distant, their light having been significantly redshifted by the expansion of the universe, and that they are likely filled with older stars and a great deal of cosmic dust. So, the cosmic question mark is almost certainly a beautiful and spectacular example of a pair of merging galaxies, a snapshot of a process of galactic cannibalism that is happening billions of light years away. But the beauty of science is that we cannot be 100% certain until we have more data. A follow-up observation with Webb spectrographs could analyze the light from these objects, measure their exact distance, and confirm whether they are indeed a single interacting system. And there is always the faint, tantalizing possibility that it could be something else entirely, something even stranger that our current models cannot yet explain. The cosmic question mark is a perfect symbol for the mission of the James Webb Space Telescope itself. It is a beautiful, unexpected, and deeply mysterious object that reminds us that for every answer we find in the cosmos, the universe presents us with a new and even more beautiful question. It is a sign that the age of discovery is far from over. The James Webb Space Telescope has already, in its first few years of operation, revolutionized our understanding of the cosmos. It has pushed our cosmic horizon back to the dawn of time. It has peered into the hidden hearts of stellar nurseries, and it has begun to taste the air of other worlds. But its journey is just beginning. Its great long-term mission is to tackle some of the biggest, most profound, and most persistent mysteries in all of science. Its greatest discoveries may still lie ahead. One of the most fundamental goals of Webb is the hunt for the population 3 stars. These are the hypothetical, very first generation of stars to have ever formed in the universe. They would have been born out of the pure, pristine hydrogen and helium gas that was created in the Big Bang. Because they contain no heavy elements, our theories predict that they would have been colossal, behemoths hundreds of times the mass of our sun. They would have been incredibly hot, brilliant, and almost incomprehensibly short-lived, burning for only a couple of million years before exploding as spectacular supernovae. These first stars are the missing link in our cosmic story. They were the engines that first enriched the universe with heavy elements, the forges that created the carbon, oxygen, and iron needed for the next generation of stars, for planets, and for us. Finding them is one of the highest priorities in modern cosmology, but they are so distant and their light so redshifted that they have remained completely beyond the reach of any telescope we have ever built. Webb, with its immense mirror and its unparalleled infrared sensitivity, is the first observatory in human history with a real, tangible chance of capturing the faint, ancient light from these first trailblazing suns. Another great mystery that Webb will help to solve is the Hubble tension. This is one of the most significant and troubling crises in modern cosmology. We have two very precise and completely independent ways of measuring the expansion rate of the universe, a number known as the Hubble constant. When we measure it by looking at the nearby universe, Using objects like supernovae and pulsating stars called Cepheid variables, we get one number. When we measure it by looking at the very distant early universe, by studying the physics of the cosmic microwave background, we get a slightly but significantly different number. This discrepancy suggests that there is something we are fundamentally misunderstanding about the universe. Webb, by using its powerful mirror to make incredibly precise measurements of the Cepheid variables in distant galaxies, will help to refine the local measurement of the Hubble constant. If the tension remains, it may be a sign that we need new physics, a new understanding of the nature of dark matter or dark energy, to explain our cosmic history. And finally, there is the ultimate question, the one that has haunted humanity for all of its history. Are we alone? Webb's long-term study of the atmospheres of Earth-sized rocky planets in the habitable zones of their stars is our first best chance to find an answer. It will stare at systems like TRAPPIST-1 for hundreds of hours, slowly and patiently building up a spectrum of their atmospheres, searching for the telltale chemical imbalances, the combination of gases like oxygen, methane, and carbon dioxide that could be the unmistakable signature of a living, breathing biosphere. The detection of such a biosignature would be the single most profound and transformative discovery in the history of science, would reshape our understanding of our place in the universe. We do not know if we will find it, but for the first time in human history, we have a machine that is powerful enough to look. We began our journey with the launch of a new golden eye, a magnificent and audacious machine, the culmination of 30 years of human ingenuity. We have traveled with it to its lonely, cold home in the darkness of space, and we have seen the universe through its powerful infrared vision. We have stood on the cosmic cliffs of the Carina Nebula and witnessed the birth of stars in breathtaking, unprecedented detail. We have traveled back to the dawn of time itself, to the edge of the cosmic dark ages, and have been shocked to find a universe of galaxies that were born too big, too bright, and too soon. A discovery that is shattering our elegant theories of cosmic evolution. We have tasted the air of worlds hundreds of light years away, finding the chemical fingerprints of carbon dioxide in clouds of sand. We have seen our own solar system in a new and beautiful light, and we have witnessed the death throes of a distant star. We have been humbled by the sheer beautiful mystery of a cosmic question mark, a reminder that the universe is still filled with surprises. What the James Webb Space Telescope is really seeing, then, is not just a collection of beautiful images. It is seeing the story of the universe, and it is finding that the story is stranger, more complex, and more magnificent than we ever knew. It is challenging our models, breaking our timelines, and forcing us to rethink our place in the grand cosmic narrative. The telescope is more than just a machine of glass and gold. It is a new human sense. It is an extension of our own innate and unyielding curiosity. It represents the very best of what our species can be when we work together to ask the biggest and most profound questions. We are living in the middle of a scientific revolution. The textbooks of tomorrow are being written right now by the faint, ancient, and infrared light that is falling at this very moment on a golden mirror 1.5 million kilometers away from Earth. The greatest discoveries are still to come, and we are all privileged to be witnesses.